So we are going to talk about the exponential series. And no, I'm not talking about the Taylor series for e to the x. I'm talking about representing any function as a sum of exponentials. Now the reason I'm making this video is that Dr. Peyam put out a video about a week ago about whether the derivative is diagonalizable. And if you don't know what that means, don't worry, we'll still make it through this video. But basically, the answer at the end is if we can represent a function as a sum of exponentials, then its derivative is diagonalizable. So in this video, we're going to be talking about whether we can represent functions in terms of an infinite sum of exponentials. Now, in order to do that, it might help to take a look at the Taylor series and see if we can get some hints from the way that that is constructed, because we know that the Taylor series works. When we think about the way that a Taylor series functions, of course we know that there's an explicit formula for the Taylor series, but the thing we're focused on is why that formula works. So if we take a look at the graph of a function, say we're looking at cosine of x. So the graph looks something like this, and our goal is to approximate that using a sum of polynomials. So we have c0 plus c1x plus c2x squared, and so on. Well, in order to do that, we might start by thinking about finite sums. For example, if we wanted an approximation of cosine x with only one term, well, if we're starting this approximation at 0, if we're looking at a constant, this constant should equal cosine of 0, so that they're the same around that point. That would be good. And then if we think about adding more terms, we might want to start thinking about derivatives. The reason for that is that if we have a derivative around 0 that's very different from the derivative of cosine x, then the approximation won't be very good. For example, the derivative of cosine at 0 is equal to 0. But if our approximation had a derivative that was positive like that, well, that's not a very good approximation at all. So in fact, we want our approximation to also have a derivative of 0. And we see that this line here is a much better approximation of cosine x. The next thing we might add is the second derivative, so that it's also curved down like cosine x. And now we see our approximation is even better, around 0. So every time we add another term, we want to account for another derivative of cosine x. And as we increase that number of derivatives to infinity, we're going to be able to approximate this function very, very well. Our goal is to take this idea and turn it into a different kind of series, where instead of using polynomials, we're looking at exponentials. So let's think about how we could do that in terms of e to the ax. So we want to be able to represent any function as a series. We'll call that series s of x, s for sum or series. It's going to be c0 plus c1 e to the x plus, and then many more terms. But what I want to take a look at is how we differentiate this function. Because remember, we're trying to account for the derivatives of f of x. We also have to look at the derivatives of our sum. So if we look at s prime of x, c0 is going to disappear because it's just a constant. c1, though, is going to stay because the derivative of e to the x is just e to the x. So our first derivative is also going to be c1 e to the x. Also remember that c0 is also c0 times e to the 0x, so that is technically an exponential. What we want to look at now, we'll take one more derivative here, s double prime of x is going to be c1 e to the x, differentiate that again, we still get e to the x back. And now I'm going to add on another term. But notice what happens in general when we differentiate e to the ax for some constant a. The result of this is that we have e to the ax, and then we also, by the chain rule, are going to multiply by a out front. So if we think about what happens when we choose a particular value of a, if we choose a value of a that's greater than 1, like e to the 2x, after we differentiate once, we get 2e to the 2x, and then 4e to the 2x, 8e to the 2x, it's going to keep getting bigger. So if we choose a value like that that's greater than 1, we're going to end up with some pretty crazy derivatives once we get down to the 10th or 11th derivative, and we just keep on going multiplying by 2. So instead, we might want to choose a constant that's less than 1, and that way, as we differentiate, the values are getting smaller instead of getting bigger. Because of that, I'm going to choose the next term after e to the x to be e to the 1/2 x. If we chose another value after that, we might choose e to the 1/3 x, and then 1/4 and 1/5, and so on. If we differentiate this, we're going to get 1/2 e to the 1/2 x, and then we multiply by c2 in here. And that second derivative, we're going to multiply by a half again. So we'll have 1/2 squared times c2 e to the 1/2 x, and so on. Now what we want to do is take this and set the first n derivatives equal to the first n derivatives of some other function. Remember that each term that we add to this series is going to let us account for another derivative. If we only have c0, we can only account for that constant. If we add c1, we can look at the constant and then also the first derivative. If we have two of these functions, then we can combine them both to account for the second derivative, and so on. So let's take a look at what we want these things to equal. For example, we want f of 0 to equal s of 0. This is the 0th derivative, and we know that s of 0 is going to equal this thing, evaluated at 0. If we evaluate it at 0, we're going to get c0 plus c1. We'll notice e to the 0 here is 1. E to the 0 here is 1 as well. So we're just going to have c1, not multiplied by anything else. And then we'll add c2, and so on. And that's going to go up to c sub n, if we're looking at the series of order n. F prime of 0 is going to be this part evaluated at 0. So we get c1 plus 1/2 c2, and so on. And if we look at our last term being e to the 1 over n times x, then when we differentiate that, we'll get 1 over n times c sub n. The second derivative, evaluated at 0, must equal c1 plus 1/2 squared c2, and so on, up to 1 over n squared times c sub n. And we'll keep doing this, and I'm going to skip down to the nth derivative of f, because that's the last one that we'll be able to account for if we have this many terms. That's going to be c1 again. If we differentiate e to the 1/2 x n times, then we're going to get 1/2 to the n times c2. And then so on, until the last one. If we differentiate e to the 1 over n x n times, we're going to have this 1 over n term n times as well, and then multiplied by cn. So this is the general form of all the equations that we need to solve for these c's. Remember that everything on the left side is a constant. All of these terms are constant too, so this is basically just a system of equations. The last thing I'm going to do here is represent this as a matrix, and then we're going to jump into Desmos and look at what these approximations look like. So if we think about representing what we have here in terms of a matrix equation, first of all, we want to take the matrix of all of the things we're multiplying out here. So if we look at c0, we're going to multiply c0 by 1 first, and then after that, there's no c0 anymore. So it's going to get multiplied by 0, 0, 0, all the way down, and still 0. c1 is always going to stay there, just multiplied by 1. So we'll have 1, 1, 1, 1, all the way down 1. Now here's where it's get interesting. c2 is multiplied by 1 at first, and then it's going to be multiplied by 1/2, and then by 1/2 squared, and then 1/2 cubed, and so on, all the way down to 1/2 to the power of n at the very bottom. So we see that every time the power is going to increase by 1 as we go down the row. The next thing would be a third. We'd have 1/3, and then 1/3 squared, 1/3 cubed, all the way down to 1/3 to the n. And this matrix is going to keep on going all the way to this final term c sub n. We notice again it's going to start with 1, and then it'll be 1 over n, and then 1 over n squared, 1 over n cubed, and all the way down to 1 over n to the power of n. This is going to be our entire matrix for what we're multiplying by these constants here. So if we make a little more space to write down the entire equation, remember this is the coefficient matrix that we're going to multiply by the constants, C0, C1, C2, C3, all the way down to Cn. And this is equal to all of those derivatives of f. So we'll have f of 0, f prime of 0, f double prime of 0, and so on, all the way to the nth derivative of f evaluated at 0. So this is the super big matrix equation for the nth order exponential series of our function f. Now, I asked Dr. Peyam and Black Pen Red Pen to take a look at this matrix equation and see if there's a way to solve it. And we haven't found a closed form yet. One thing Dr. Peyam noticed is that if you look at this bottom right corner of the matrix, starting at this 1 here, this is something called a Vandermonde matrix, and it has some pretty interesting properties that might let us solve for these constants. But I have not been able to find a closed form beyond just using this matrix equation and solving for the constants directly. So now let's jump into Desmos and take a look at what these approximations look like. So we're going to look at a couple of these approximations in Desmos now, and since Dr. Peyam suggested looking at sine of x, we're going to take a look at cosine. Of course, using sine would produce a similar result for these approximations. So I'm going to use the approximation with 3 terms, and then after that, we'll take a look at the approximation with 8 terms to see how they compare. So the first approximation with 3 terms is -1 minus 2e to the x plus 4e to the 1/2 x. And we see here that it's a pretty decent approximation around the value of 0. We see that the first 2 derivatives are equal with this approximation and with the function cosine of x. But pretty soon it ends up being not very close to that original function cosine. So now we'll take a look at the approximation that has 8 terms. And one thing that we have to remember about this approximation is that the constants are going to change as we increase the order of our approximation. And that's a little bit different from Taylor series, because when we're looking at Taylor series, the first 5 constants, if we know those, we can just add on the 6th constant. But when we're looking at these exponentials, we have to go back and change all of those constants that we had before to account for the new term, because the exponential functions aren't equal to 0 like the polynomials are. And what you'll notice here is that when we have an 8th term approximation, the constants end up getting super, super big, up to something like 3 million for one of the constants. And you might ask, mu prime, why would it be useful to have an approximation if 8 terms is going to give us a value of 1 million for one of the constants? That seems kind of ridiculous. One reason is that it's just really cool to know that we can approximate functions like this. But the other reason is that it lets us show that the derivative is diagonalizable, like I said at the beginning of the video. But now we're almost done. We're going to take a look at this approximation with e to the 1/7 x, and now we can see the glory of this exponential series. So after 8 terms, we see around 0, the function is very, very close to cosine x, but even looking farther out, as far out as between -3 and 3, these values are fairly close, and it's much closer than that original 3-term approximation. What that means is, as we add more and more terms and account for more derivatives, our approximation is going to get closer to that function of cosine x, and it's going to stay close for a longer range. So as we increase the number of terms up to infinity, that will allow us to write cosine just in terms of exponentials. Now we're back at the board, and if you're interested in this exponential series idea and you want to try it out on a few different functions yourself, I've written down this matrix equation here so that you can do so. This 5x5 matrix is the inverse of the coefficient matrix for these c's when we have 5 terms. So if you take this 5x5 matrix on the board and you multiply it by f of 0, f prime of 0, f double prime all the way down to the 4th derivative at 0, multiply these two together for any function f that you like, plug in these numbers, and you will get a vector that has all of the values for c0. And then you can write your series approximation s of x as c0 plus c1 e to the x plus c2 e to the 1/2 x, and then plus c3 e to the 1/3 x plus c4 e to the 1/4 x. And again, you can plug this into Desmos and see how those functions do. I've tested this out on f of x equals x and x squared and even e to the x squared, and they all seem to do pretty well. Of course, there are a few functions that won't behave so nicely. So for example, if we look at the natural log of 1 plus x, this will not have an exponential series that works super well, because as x goes to -1, we're going to get the natural log of 0, which is -infinity. So just like the Taylor series for this natural log only works between -1 and 1, the same applies for that exponential series, that it won't expand out all of the way. But besides that, if we have a nice infinitely differentiable function that doesn't have any discontinuities or singularities, I think this exponential series will work really well. And as we increase the number of terms to infinity, if we take the limit of that sequence of functions, it looks like those will approach the actual function that we have. So that is the exponential series for any function.